Hello, now we move on to another type of oscillator circuit, which is a tuned oscillator. In tuned oscillator, we'll learn first about the Colpitts oscillator, and later we'll move another type, which is the Hartley oscillator. So first, with Colpitts oscillator, you should be able to describe the operation and draw the waveform associated with it, analyze the circuit and derive the transfer function, determine the frequency of oscillation, and know how to design a Colpitts oscillator. LC oscillator or tuned oscillator usually is used for generating a sinusoidal waveform for frequency above 1 MHz. The most famous will be Colpitts and Hartley. Beside that, we have Clapp and also Armstrong, crystal control oscillator, and Pierce. LC oscillator is based on the tank circuit. So if you look over here, we have inductor and capacitor and voltage supplier. Once we close the switch over here, this voltage will supply and it will charge the capacitor. Once this switch is open, this capacitor will act as a battery and it will energize the inductor. So with this, the capacitor will discharge the voltage across the inductor. And what you'll get the output, initially you have a very high amplitude, but slowly it will dies out. Okay, so it will ring, but it dies out because there is no energy pumped back to the tank circuit because we open the switch over here. So this is the example of Colpitts oscillator. It consists of two capacitors, C1, C2, and inductor. C2 is the one that is connected to the output, while C1 is the one is connected to the input of the amplifier. In this type of circuit, this is the common source amplifier. Okay, so usually the Colpitts oscillator use a JFET because it can tolerate with a high frequency. Okay, the frequency of oscillation Fr or F0 equals 1 over 2 pi square root of LC equivalent, and the C equivalent is these two capacitors, C1 multiplied with C2 divided by C1 plus C2, and the ratio of gain is C1 over C2. We'll learn how to derive this equation. And this is another type of Colpitts oscillator. We have a JFET over here with RFC, radio frequency choke, and you have two capacitors, C2 connected to the output, C1 connected to the input with one inductor. So this is the feedback network for the Colpitts oscillator, and this type of oscillator is introduced by Edwin Henry Colpitts in 1918. So it will generate a sinusoidal waveform at a very high frequency. This is another type, Colpitts oscillator. This is inductor couple. Okay, you have C1, C2. Again, C2 is the one connected to the output of the transistor. C1 is the one connected to the input of your transistor. This is a bipolar junction transistor or BJT. Okay, you have two capacitors, C1, C2, and one inductor as the feedback for the Colpitts oscillator. But for our topic, we'll look into the Colpitts oscillator using an op-amp. Actually, the op-amp will limit the frequency of oscillation. This is just to show the analysis of a Colpitts oscillator. So, how to remember it is a Colpitts oscillator? You have two capacitors, okay, but one inductor. C2 is the one connected to Vout, C1 is the one connected to input. You must look closely the position of C2 and C1, okay? And in order to analyze this circuit, remember just now, the node over here, VF, is connected to the input of your amplifier. Usually, the value of RA over here is much greater compared to the reactance of this capacitor. And usually, RA is 10 times of XC1. With that, we can assume the current over here is very small, or we can say that it is 0, and we can ignore this branch. So you just left with the two capacitor and one inductor, and this will simplify the analysis of the Colpitts oscillator. The feedback network just consists of C2, C1, and L because we assume the current just now to be 0. And we can redraw the circuit to be like this. These two in series, L, C1, parallel with the C2. And if you look over here, the impedance looking at this particular node, we can get the total impedance to be C2. So the impedance is minus JXC2. It is parallel with L in series with C1. So JXL minus JXC1. Okay, so it will be minus JXC2 multiplied with JXL minus JXC1 divided by minus JXC2 plus in brackets JXL minus JXC1 open the parenthesis. So this multiply with this will give minus j squared xl xc2. This multiply with this will give xc1 xc2 because j squared is minus 1. Okay, and at the denominator minus j, this is plus j minus j. So rearrange this equation. Everything is j in bracket xl minus xc1 minus xc2. So you have two part. The real part, the numerator, the denominator is an imaginary part. Okay, so set the imaginary part to be 0 in order to find the frequency of oscillation. So xl minus xc1 minus xc2 equal to 0. So with this, xl equals to xc1 plus xc2. Substitute xl as omega L. xc1 is 1 over omega c1. xc2 is 1 over omega c2. These two added is equals to c1 plus c2 divided by omega c1 c2. So you have omega L equals to this. Omega equals to omega squared L. c1 plus c2 divided by c1 plus c2. And this is, I equate it to 1 over C equivalent. So from there, the frequency of oscillation omega naught is 1 over square root of L C equivalent, and F naught equals to 1 over 2 pi square root L C equivalent, where C equivalent is C1 C2 divided by C1 plus C2. Okay, the feedback just now has been redrawn that clearly shown that LC1 is parallel with C2. Your VF is actually just the voltage across C1. So from this node to the ground is actually your VO. But from this node to the ground across C1 is your VF. So using a voltage divider, you can write your VF is simply VO multiplied with minus JXC1. So VO multiplied with the capacitor over the total impedance. Okay, VO multiplied with minus JXC1 divided by minus JXL minus JXC1. These two is in series. Okay, so simplify this equation. J cancel out. So you're left with minus XC1 divided by XL minus XC1. I bring VO over to this side. So VF over VO is your beta, and it equals to minus XC1 over XL minus XC1. So with this, you know that just now at the frequency of oscillation XL equals to XC1 plus XC2, we get this when we equate the imaginary part to be 0. Substitute into this equation, substitute XL, okay, with XC1 plus XC2. Simplify this equation. XC1 minus XC1 will cancel out. So you left with minus XC1 over XC2. Okay, or XC1 is 1 over omega C1 and XC2 is 1 over omega C2. So simplify this thing, you'll get that your beta is equals to minus C2 over C1. There is a negative sign over there indicating that VO and VF is out of phase by 180 degree. Since the beta just now is an inverting type, so your amplifier must also an inverting. It must introduce 180 phase shift. So with this, your VF coming to RA, you have RF going into the negative input of your op amp. So A will be minus RF over RA. Remember, beta multiplied with A must equals to 1 for Barkhausen criteria. So beta just now, you have C2 over C1 and A is RF over RA. I just take the magnitude, equate it to 1. So for Colpitts oscillator, okay, the magnitude of A, which is the ratio of RF over RA, must equals to the ratio of C1 over C2. So look clearly, it is C1 over C2. C1 is the one connected to input and C2 is the one connected to the output of your amplifier. You cannot be confused about this because it will give a different value for A if you interchange C1 and C2. Okay, so for Colpitts oscillator, in order to produce a sinusoidal waveform, you must remember the amplifier over here is a inverting amplifier with a gain minus RF over RA. This is your RF RA. Your beta over here is minus C2 over C1. And in order to design that, the ratio of RF over RA must equals to the ratio of C1 over C2. Your F naught will given by this feedback network, the circuit in the bottom, and F naught equals to 1 over 2 pi square root of L C equivalent, where C equivalent is C1 C2 over C1 plus C2. So this is how to design a Colpitts oscillator. You must make sure that the ratio of RF over RA equals to the ratio of C1 over C2. And with that, you can produce a sinusoidal waveform at this particular frequency. Thank you.